Alright, these are your 8.3 video notes for day 2 of polar form of a complex number. In this day we're going to talk about powers and roots and how we can use polar versions or polar formulas to help us solve problems that algebraically would be fairly complex. So let's start by looking at what our first problem is, which is an exponent problem. And then we'll do roots in a little bit. If you took a complex number, so negative root 3 plus 3i, and you raise it to the 6th, algebraically you would have to do this. That is a lot of work. That's a lot of FOIL and double and triple and so on distribute, and it's just like kind of a big mess. So while it can be done, we've developed ways that are easier by going polar form. De Moivre's theorem is the exponent formula that'll do this problem for you, and a lot less work and real slick by just doing a little bit of polar conversion. So what we're going to do is just discuss the formula for a second, and I'll show you guys how it works. You notice you need r and you need theta, so again, here you go. There's our r and theta calculations. The n, which is your exponent, then is applied to the radius and then multiplied by the theta. And so by using this shortcut formula, we can get the solution to this fairly quickly without a lot of work. So let's get into a couple examples of that to start. So my complex number, minus 4 plus 4 root 3i to the third. Now to do this problem algebraically probably wouldn't be terrible to multiply it by itself 3 times. But let's just run through and see how it goes in the polar form. And then we can take it back and see what it would be as a rectangular answer. So things to remember before you get going, especially when you get down to theta, is what quadrant is your original complex number in. So make a note to yourself that's in quadrant 2. That's important when we go to do theta. We want to choose in the same quadrant. R is our calculation. We've done that plenty of times. You guys should be good at that. Tangent of theta, b over a. Negative root 3 comes from doing square root of 3 over 2 over 1/2. And as a coordinate, that's 1/2 and square root of 3 over 2. So I know that's going to be a pi over 3 coordinate, and then in quadrant 2, that's going to be 2 pi over 3. And then n is my exponent. Now that's not something you got to necessarily jot down, but just making sure you guys are clear on what is the n that we're going to use. And then it becomes a formula-based problem. So really it's pretty simple at this point. You plug in, so I'm using 8 to the third, so there's radius to the exponent times theta, exponent times theta. Then we clean this up a little bit, so let's just do the cleanup part of this. So that's 512, cancel my 3's. And then this would be the polar form of the answer, the solution to this. Now to find out the solution rectangular, we actually can take it back, which means we would do the cosine of 2 pi, which is 1, and the sine of 2 pi, which is 0, and then distribute the 512 in and get our solution. Now what this number represents, or answer represents, is 512 plus 0i, which is the answer algebraically to doing this work. Now I know that work, as you look at it, might not be terrible, but in comparison to doing find r, find theta, plug it in, clean up, I still think this is better, and especially as this exponent gets bigger and this work gets to be even worse, then this is way better. But if you want to track this, I foiled the first two. That's this work. Remember, I squared is -1, so you combine your number terms and your I terms. Then another round of FOIL with the last one. Clean it all up, and you get there. Like I said, not terrible, but I still think shorter with a polar version of it. And then you can always go back and see what it would be as a plus bi. Okay, so pretty straightforward actually, just a formula, right? Let's try a couple others. So again, as you start the problem out, think to yourself, quadrant, just so you're clear on what you're going to use when you go down to do your theta. Otherwise, r again, straight calculation, tangent of theta, b over a. Quadrant 1, that's a pi over 6. That's like doing 1/2 over the square root of 3 over 2. So that's my pi over 6 coordinate. And then keep track of my n and dump them in, and away we go. So again, take your r, raise it to the exponent times theta. And then we'll clean this up. So 2 to the 5th, 32, 5 pi over 6, 5 pi over 6. And then again, we can take it back. So this is actually an answer. It's a polar form of the answer to doing this. And like I said here, no thanks. I don't want to do this 5 times algebraically, so I'm not even going to bother trying to show you guys that or do that one. It's just too much work. But if I want to take it back, I certainly can. Cosine of 5 pi over 6, negative root 3 over 2, sine of 5 pi over 6 is 1/2. Distribute the 32 in. What this represents is the answer to this, or even, I guess more importantly, it's the answer to this. But the work to get you from that to this is enormous compared to doing it in a polar format. So again, a nice way to get there without a lot of work. And a pretty easy formula to work off of. Chances are you guys will be asked in WebAssign anyway just to give us this answer. It'll accept either one. It'll take the black one. This one would be the polar form of the answer This would be the rectangular. And probably you'll be doing the black, but to show you that we can go back if we want to. Okay, we're only going to do just a couple of those. Let's move on to roots. Roots is a little bit more complicated in terms of just maybe explanation. Also the formula. It's got a little bit more going on. Before we get into the formula, what we want to do is just talk about, what are we saying when we're finding roots? Roots are solutions. And we've asked you guys to solve equations in the past. We probably didn't use the word find the roots, like solve the equation. So what are the solutions? Because the directions were to solve, right? The directions here are going to say something about roots or solving, but solving is really finding roots, especially when you're talking about exponents bigger than 2, even with 2. Let's talk about some algebra for a second. So the incorrect way to do this would be this. And the reason this is incorrect is because, it doesn't seem incorrect, right? You add 1, you take the fourth root, all seems good. But my question here is how many solutions should there be? How many roots should there be? And if it's to the 4th power, I should have 4. And I'm only producing 2. So where are the other 2? Well, because of the method you chose here, you actually lost 2 of your solutions. So that would be incorrect way of doing it. It actually is an okay way of thinking about it. I'll come back to that in a minute. Algebraically, the right way to do this would be to factor. So I'm just using a difference of squares here, and then I'm getting all 4 solutions now. This is the square root of -1, which is plus and minus I, and then the square root of 1 plus and minus 1. Now I got all 4. But what is it that I was actually finding when I found my solutions? I found the 4th roots of 1. Again, not correct algebraically, but it's definitely the correct way of thinking about what I'm supposed to get. 4 solutions, 4 roots, the 4th roots of 1. Now, algebraically, wow, it seems pretty easy, so what about this? And here's where your polar is going to help you out when you're trying to do something that's a little bit more complicated. What are the 6th roots of that number? I'm thinking about it again algebraically as what I'm trying to find. Not this is correct way of solving, but it's the correct way of thinking. I want to know what are the 6th roots, the 6 solutions when I solve for z. So z equals the 6th roots of, okay, that's what we're looking for. So keep that in mind as we go to do our work. A lot of your problems will actually read as a statement. It'll actually tell you, like, just like this, find the 6th roots of. And in your back of your head, it's like, well, what am I actually solving for? I'm solving this equation. And then some will actually read like an equation, which we'll do too. So we'll show you like the equation style and the 2 different versions. We're going to start with the one that's in words, just to get you going with a formula. And then we'll switch over to the equation style, even though that's really the same problem, just a different way to start. So let's talk about formula for a sec. So the formula looks a little bit more heavy duty than the exponent formula. It's not really. It's just there's more going on. I'm supposed to just up front start plugging things in. But you notice you got an R, you got a theta, you got an N. So the same 3 things you had to find in the first problem. The N here actually represents which root we're going to figure out. So a cube root is an N of 3, a 4th root is an N of 4, and so on. When you're going, this WK is basically a symbol for my roots. When you go to find them, we actually got to start with W sub 0. Now, it'll be more obvious here in a minute, but the reason for that is that if you put a 0 in, if you start with 1 here, then you're actually going to the next root in the list and not doing the first root, which is if this is 0, this is gone, and there's the first root. What the formula does, it finds the answers by location, by using a radius and an angle of rotation. And then again, it could be turned back into a plus bi if we wanted to see what that answer would be. So it basically, if you got 3 roots, you're going to go a third of a way through the rotation each time and figure out the location of each root. And then again, we can convert it back. Okay, it's much better to see the problems in action, so let's see the problems in action here. So this one reads as a statement, what are the cube roots of? So what I'm doing is solving an equation that would be z to the 3rd equals this. And then I'm trying to find the cube roots of it. But again, start out with R and theta. Keep track of quadrant. This is quadrant 1, so when I go to choose my theta here, also quadrant 1. That's quadrant 1 because positive, positive. And then N is 3. So what you're going to do now is you're going to set up a formula that's customized for this particular set of numbers. So it's unique to having this radius and this theta for this number. And so you see my R raised to my exponent. Sorry, my R is raised to an exponent, but actually that's really a cube root, so to be clear on that. And then my theta plus 2k pi over 3. Again, N being my 3 roots. The 2k pi, if you guys remember that, going back to solving trig equations, is basically creates a multiple, and that's what gets us to jump from one answer to the next. So we'll get to that in a second. Now I want to clean this mess up, make it a little bit nicer. So 2 to the 1/6, that comes from this being 2 to the 1/2 actually, and then 1/2 to the 1/6 to the 1/3, excuse me, is 1/6. Pi over 4 over 3 is pi over 12, and then 2k pi over 3, 2k pi over 3, and then we do that in both spots. So what I've done now is create a custom formula that's unique again to this information that'll allow me to generate the solutions or generate my roots. Generating roots always start with W is 0, which means 0 has been plugged in right here, which knocks that out, which is why my first angle is pi over 12. In terms of what I just figured out, if I took 2 to the 1/6, which is a radius, and I rotate to pi over 12, it's a location of the first solution or the first root. And then what I can do, which we're not going to do just to save a little time here, but I could definitely, because they're not unit circle angles, I'd have to go to a calculator. But I can do the cosine of pi over 12, and I can do the sine of pi over 12, and then distribute in 2 to the 1/6 and get a plus bi looking answer. And it would be one of the 3 roots in a plus bi form. But again, we're not going to do that just for the purpose of saving us some time and calculation. Unless these are unit circle angles, like over 4 over 3 over 6, then we could, and it would be quicker. Then 1 and then 2. Now, to get these really quickly without having to do a lot of work, what you don't want to do is plug in a 1, then plug in a 2, common denominator, and do them individually. What you want to know is what is your multiple? What are you adding each time? And that's real simple. We've done this before. So if it's 2 pi over 3, and I go to 12ths, this is 2 pi over 3 in 12ths. Then all I got to do is go like this and add my multiple, excuse me. So if you do 1 plus 8, which is 9 pi over 12 reduces. And then if you do 9 plus 8, which is 17, and then I can crank out my answers pretty easily without a whole lot of extra thought going on. So that's the easy way to get the roots or the solutions figured out instead of doing one at a time by plugging in k is 0, k is 1, k is 2. So this is an important thing for you guys to understand. Like, what is that? Where does it come from? That's 2 pi over 3 with a common denominator of 12. And then just add my way down the list. Okay, let's do a couple more. We'll show you one more where we have a statement, then we'll do one that's a solving question, then we'll wrap it up. So the 4th roots of 16i. Now, when I go to this, my first thought is radius is countable and theta is visual. And so I didn't need to do any kind of calculation because it occurs to me that 16i is a complex number that sits on an axis. So it really would be 0 plus 16i. And 16i would put you up here. And so I know it's a countable distance for a radius. And I know just by visualization it's at pi over 2. So that'll speed up your work a little bit. Let's generate our formula. So 16 to the 1/4, 4th root, divided by 4. There's my theta, plus 2k pi. Clean up the formula. So 16 to the 1/4 is 2. Pi over 2 over 4 is pi over 8. 2k pi over 4 is k pi over 2. So this is a custom formula for this information. And then I know I'll have 4 roots. I'll start at 0 again and start cranking out solutions. And we'll go back and talk about these in a second. So again, if you plug in a 0, that eliminates the k pi multiple, which means your first angle will be pi over 8. Then what I'm using to generate the rest is my multiple, right? So what I'm saying is pi over 2 with a common denominator of 8. This is pi over 2, common denominator. And then I can just go like this. Add 4, add 4, add 4, until I get my 4 roots generated. Much faster way to go than literally plugging in k is 1, k is 2, k is 3, and trying to do them individually. And then again, over here pops up the solutions by location. So this is radius 2, rotate to pi over 8, and then if I, again, did the calculation of all this, I would give myself the a plus bi format, or the answer to this as the 4 roots in a rectangular form. So, and we're not going to do that again just for the purpose of saving ourselves some time and not having to go to the calculator. Okay, let's talk about the last problem. So the last one involves an equation, and again, it's good to, even though this isn't correct, a couple things here. This isn't the correct way of solving, doing the 4th roots. That's what it means, right? So what I'm thinking is if I add 1 and take the 4th root, I'm finding the 4th roots of 1 plus 0i. Again, this is going to be nice because it's a axis coordinate, so again, countable, and visualization tells me that, and then start generating my formula. So a little bit different start in terms of thought process, but the same work. So my radius to the 1/4, 4th roots, 0 divided by 4, clean these things up. And then I'm going to my polar form, so there'll be 4 roots. Again, we'll talk through these in a sec. And again, you could use your multiplier. I think this one's a little bit easier because you probably could actually plug in the k. If k is 0, you get 0. If k is 1, k is 2, 2 pi over 2. If k is 3, 3 pi over 2. So in that case, the k might be beneficial just to use. Or I could just go add my way down the line and then turn them back into. Now earlier we had talked about the 4 solutions were plus and minus 1, plus and minus I, and we solved it algebraically by factoring. And you notice that here they are the same solution. So we can always turn it back into rectangular and check it out. Okay, so again, the idea of the formula is to generate solutions in a polar form for a problem that would be much more complex for us. And that's the end of our notes for today.